Hi, and welcome to Chapter 3 of Computational Linear Algebra. Today we'll be talking about lines in 2D. So, outline of what we'll talk about. We'll introduce 2D lines, we'll have a formal definition, we'll look at three different representations, parametric, implicit, and explicit. Then we'll look at converting between parametric and implicit equations, talk about how to use some of those equations to compute the distance of a point to a line, talk about the concept of the foot of a point, projection onto a line, and talking about intersections. And then we'll go back over some terminology. So lines are the building blocks for many geometric constructions. Two sets of parallel lines might be overlaid in the graphic you see here are called a Moiré pattern. It's used in optics for checking properties of lenses, and it's really about how the two sets of lines interact and form other patterns. The focus of this chapter, however, is not on Moiré patterns. It's on how do we actually represent lines, compute things with lines like distances and intersections. Okay, but lines are a fundamental part of what we do, and you get lots of interesting things that you don't necessarily expect just from lines, as you see from these Moiré patterns. So how do we define a line? Intuitively, most of you have an idea what it is. A line is a geometry in 2D. A line has 2 points, and those 2 points define a line. And we want to be careful to differentiate between a line segment, the section between those 2 points, or between 2 points, and a line, which is an infinite structure that goes through those points. In fact, we can define it not just with 2 points. We can also define a line by having a point and a vector that is parallel to the line. We can, in fact, have a point and a line and a vector that is perpendicular to it. In fact, we could choose any fixed angle we wanted and have a point and a vector at a fixed angle with respect to a line. Any of those could represent it. Okay, so we talk about this representation where we have a point and a vector that is perpendicular to the line, or the normal to the line, as a particular representation because it has lots of nice properties when we go to talk about things later. But given any 2 points, we can have a line. Quick question. Can you make a line with 3 points? Well, you can. In general, 3 points don't have to lie on a line, but they might. If I chose this point here, the halfway point between these 2 points, obviously it would still be on the line. So 3 points might lie on a line, but in general in 2D, 3 points do not lie on a line. We can talk about the concept of a family of lines. One kind of family of lines is all the lines that share a common point. And then you choose any second point, you get another set of lines. So all of these lines or line segments all have a common point in the middle and then different points on the outside. Another kind of family of lines could be a family of lines that all share the same normal. And if they share the same normal, but they go through different points in space, then they end up forming parallel lines like we see in this kind of structure here. We can define other kinds of families. Families really come from having a representation and saying, I'm going to make them share some property within that representation. So you might think about what other kinds of families could there be. Might be easier after we talk about other kinds of representations, and then we can come back to that. So let's talk about the parametric equation of a line. This is one of the easiest representations to work with. It is commonly used in graphics because it is easy to use to generate points in the line. So given some point and some vector, we can then define the line as the point plus t times the vector, where t is then a parameter that specifies where we are on the line, hence the parameter or parametric representation, because t is our parameter. So I can start at some point p, and that's the same as having t equals 0. I can make t equals minus a third or make t equal 1, and I get from p to q, right? Where q is the vector, q is the point such that q minus p equals v. We can see that from the parametric representation. So the nice thing about this from a computing point of view is you can step along this line by simply choosing new values of t. If I want to draw 10 equally spaced points, I might choose t equals minus 5 to 5, and I'll get 11 points, because if I go to 0, minus 5 to plus 5, I'll step 5 points to the left of p or above p and 5 points after it. So this makes it easy to do lots of things in the computer. So given the parametric form, we can also talk about it in terms of barycentric coordinates. So if we think of v as the vector q minus p, then I can also write this as 1 minus t times p plus t times q. So this is a parametric representation where I'm actually representing it not with a vector but with 2 points. And this just becomes an efficient way of representing it given 2 points. I can compute v and then use it, or I can just use this representation. And then in this form, 1 minus t and t are the barycentric coordinates. This type of form is called linear interpolation. Some people use the word interpolation only when t is between 0 and 1, and extrapolation when t is greater than 1 or less than 0. So if we look at them, these idea of barycentric coordinates, the sum of the coefficients is always 1. So this gives us the idea of having points in between. This is a convenient way of representing then a parametric line segment, because t is just going to go from 0 to 1. This is a convex combination, and in this formulation people often talk about t being between 0 and 1, and as I said, we call that interpolation. If t is less than 0, then we generate a point on the line that's behind p. If t is greater than 1, we generate a point that's past q, and we can call both of those areas extrapolation. And they have different meanings. Interpolation between 2 points is not a bad representation sometimes when you're trying to estimate the values between them. Extrapolation becomes a little tricky, especially if you take t to be very large. If you give me 2 points and ask what's the point on the line, between them you do pretty well. If you ask about t equals 1 billion, all of a sudden you might get a lousy estimation of what's really going to happen in the future if you try and estimate this as a model. Parametrics are very good from computing points on the line. As I said, we can just basically take a bunch of equally spaced parameters. In this case, we were going to do t going from I divided by 9 from 0 to 9, we get 10 points, and then you can step out and you get equally spaced points. And another way of thinking about this is the parameterization can also be the speed at which you do things, and so you can play various games. The points, of course, don't have to be equally spaced. I can make points that are spaced differently along the line and get different effects. Another kind of representation of a line that's very useful for certain kinds of computations is the implicit equation of a line. And we call it implicit because we can't actually tell you explicitly which points are on the line. Okay, we define the line, the implicit representation as a dot, or the dot product we talked about last class, x minus p equals 0. And so this gives us an equation, and it's implicit because whenever a value x satisfies this equation, then we know what's on the line. And in this representation, a is normal to the line, so it's perpendicular to the line, and x minus p, so p is some point on the line, x is a point that is being used here, x minus p and a are perpendicular. We know that because their dot product is 0, and as soon as their dot product is 0, the only points that are going to have that property are going to be on this line. And so you can sort of see this is another way of representing it. We're using the dot product property to say, given any x, if x minus p dot a is 0, then you're on the line. And this is also called the implicit equation of a line, the point normal form of a line, called point normal because it's point and a normal. Okay, you can expand this and you can write it out as a1 x1 plus a2 x2 plus or minus a1 p1 minus a2 p2 equals 0. That's just expanding out the dot product. And if you combine all those things, you can represent that this is effectively a1 times x1 plus b x2 minus c equals 0, where these two here, because they don't depend on x, are combined into a value. Okay, so you may have also seen this in a 2D equation as ax plus by plus c equals 0, which is another implicit form of a line. In this form, given any point, x1, x2, you can test if this is true. This is a little harder to see exactly why this is points on a line. The point normal form makes it clear because of the dot product relationship. Okay, so what can we do with this? Well, first, let's actually generate form. So given 2 points, P and Q, 2, 2 and 6, 4, we can find the implicit representation by taking Q minus P. That gives us the vector from P to Q. Now we want to take the normal. We compute the normal by just inverting the coordinates and negating 1. So the normal here is minus 2, 4. And then C, which we get out of the equation, is just 2 times 2 minus 2 times 4 because of the values involving P. It's minus 4. And so the implicit equation of the line is minus 2x1 plus 4x2 minus 4 equals 0. Now this is not point normal form. Think to yourself, what would point normal form be? Okay, here's A, here's P. We'd simply take A dot x minus P equals 0. Okay, and we can just leave it in vector form like that if we wanted to with the dot product. And it still gives us a usable form for the equations. Okay, now why do we actually care about the implicit equation of a line? Well, imagine that I'm doing operations where what I really want to know is this point on the line? And that turns out to be what the implicit equation is really good for. Parametrics let us give you points on a line. Implicit lets us test whether or not you're on the line. So given some point x, you just plug in this equation, and if f is equal to 0, it's on the line. Okay. Now, how much you be using this? Well, you might be trying to decide if, say, in your game, one object, the corner of an object or the bullet is about to hit the target. If it hits it, then it's going to be there or it's going to bounce off the wall. There's lots of things. It becomes more useful when we get to higher dimensions, but even in 2D, trying to figure out when one point is on the line is very useful. And now we want to be a little careful from a computational point of view, this thing that if f equals 0, if you try and implement that in programming, you often have a problem because if I'm using floating point numbers, f might not equal 0 with floating point precision. What we really want to do is have some idea of a tolerance. So if I'm using standard floating point, I might actually say if the absolute value of f is less than 10 to the minus 7th, which is the precision of a single precision number in general, then I'm on the line. And that tolerance is needed because there's what we call round-off error, which we'll talk about again later in the semester. But it's important to know that if you actually tested in C code or C# code, f equals 0, it might not be true ever for your line because there might be no easy place to get it if I'm stepping around in fine places, but it might be really, really close. The tolerance is important, so the true meaningful way of looking at it is to think about f divided by f, the value that I got, divided by the magnitude of a, where a is the normal. And the reason for that is if the normal a becomes very, very large, then I'll change my round-off error. So although I said before 10 to the minus 7th, that would actually work out fine if the norm of a was about 1. So if a was a unit normal, then you could just say, well, if f is less than 10 to the minus 7th, then consider the absolute value is 10 to the minus 7th, you'd be fine. And then actually, although I said absolute value, it turned out to be interesting because the sign of D indicates the side of the line that the point is on. So if in this drawing here, I can talk about the positive side and the negative side. So not only is the implicit equation of a line going to tell me whether or not the point is on the line, I can also use it to figure out what side of the line you're on. So if I'm trying to decide is the spaceship inside the docking station area or not, and the docking station is a line or a couple of lines, I can check whether or not it's on the positive side of each of the lines. So imagine a square. Square's got 4 lines. For each of those, if you're on the positive sides of the square and you've defined the normals properly, then you can test whether or not you're inside or outside of that polygon object. Finally, the last form is something that you've probably actually all are used to. This is the form of a line that is often given in high school classes called the explicit equation of a line. And it's where we basically say y equals mx plus b, or x2 equals, in this case, a divided by b, x1 minus b over c, which you can simplify to x2 equals a x1 plus b, or y equals mx plus b. where here you have the geometric interpretations of rise over run. So A is the slope, and B is then the intercept with respect to the vertical axis, sometimes called y. Here we're going to call it E2. The drawback of this is it becomes very difficult when you want to draw a line that goes up. Vertical line has infinite slope. There is no representation of A. It causes you problems. From a computational point of view, we're going to see another problem. Even if you never have a perfectly vertical line, as the line approaches vertical, it's going to give you numeric problems. In fact, as a general rule of thumb, anytime you have a special case for computing, like you can't do this if A equals 0, you can't do that if, in this case, B is 0, that's why you get the infinite slope. In floating point, as you approach that area, you might also have a problem, so you have to be a little careful. So implicit equation of a line, although it's easy to interpret this idea of rise over run and intercept, it's not very general, so we won't use it very much. Okay, so since the two we're most interested in are parametric and implicit, parametric lets us generate points on the line. Implicit lets us test whether or not you're on the line or what side of the line you're on. And so depending on what algorithm we're trying to do, it may be convenient to convert between one or the other. Okay, and so make sure you understand. We already showed an example of how to convert from parametric to implicit. You usually be able to go both ways. And as I said, we'll ignore the explicit form because it's not very useful for general 2D geometry. And we're only going to stay in 2D for a while. Once we get to 3D and 4D and 15D, explicit is not going to be so useful. Why not? Why don't you think it'll be useful when we get to 3D and 5D? Well, part of what made implicit useful was this concept of rise over run, which makes sense in a 2D drawing. It becomes a lot more complicated to talk about those same concepts as you get to 3D, let alone 4D and 15D, where it's going to turn out parametric and implicit are going to be easy to represent in as many dimensions as we need. Okay, so let's go back and look at how we do parametric to implicit representations. Given a parametric line, right? So we have P plus T times V, point normal form, point plus vector form. We want to find the coefficients A, B, C of the implicit form. So how are we going to do this? Well, first step, which we talked about before, we're going to form a vector which is perpendicular to V. So we're going to take A, which is minus V2 over V1. This just gives us the perpendicular to V. And then we're going to determine the coefficients A1, A and B by putting that in the A dot X minus P form, computing out the coefficient C, which is A1 times P1 plus A2 times P2, take the minus sign of that, and we can put that into our equation for the coefficient. What was A? Think back. Okay, what was B? If you're not sure, go back and review your notes. Okay, so how about going the other way, which we didn't do before? Given an implicit, how do we get the parametric? Okay, so given we have ax1 plus bx2 plus c equals 0, we want to find P and V. So we need to find one point on the line and a vector parallel to the line, and that'll give us what we need to do. So it turns out, and we're not going to show you how, it's relatively easy for you to go derive that this is true in general. If this is an implicit equation, then the vector b divided by minus a is perpendicular to the a that went into this equation. Okay, now you just draw this out in vectors and you'll sort of see where it comes from. Remember, the a and the b and the c here came from taking the dot product of a times x minus p, and so x1 and x2 came from the first element of that dot product. Sorry, x1 and x2 are the coefficients that came out of that. So the vector a is actually a over b. And so the gating and flipping the two elements gives us the perpendicular again. So candidates for the points we want to do, we can actually consider the intersection with either the E1 axis or the E2 axis. And there's 2 points that could do this, minus c divided by a or minus c divided by b. We can't necessarily decide a priori looking at it which of these is going to be better. What problem might we run into? Why might not one of these exist? Well, if the implicit line is parallel to, say, the E2 axis, then B will be 0, and I'll have minus C divided by 0, which is a nonsensical term, so we can't have this all the time. So in fact, in pragmatic terms, since there are 2 points we could choose, for numeric stability we choose the intersection that is closest to the origin, that is the smaller of these two numbers, either the smaller of minus C over A or minus C over B, which is the same as choosing the larger of A or B. And that'll give us the most numerically stable representation for our parametric line. Okay. Now, are those representations unique? No. Why? Well, because in fact, especially for the point vector, it becomes pretty obvious. I can choose any point on that line and any vector. And since I can scale vectors, and I have lots of points, I'll get two very different representations. Now that's one of the disadvantages of the parametric representation of a line. I might not be able to tell if the two lines are the same. They might look very different, but actually describe the same line in space. And so a way of testing, if I want to check if two lines are the same, are to actually convert from parametric into implicit, and then back from implicit into parametric. And if we use this convention, where we choose the numeric stability, okay, are we going to get always the same representation for a line? Okay, so we have here a unique way of choosing between these two intercepts. Will we always get the original line? No, even that doesn't give us the same representation. Why? Because in this step here, we chose a perpendicular to A. But this perpendicular doesn't have to be unique. If I multiplied both A and B by 2, I'd get another unique, perpendicular. Okay. So given this representation, is this unique? Given the implicit representation, is there only one, for a particular line, is there only one set of A, B, and C that are always going to be the same, equal to 0? Think about why that might be the case. Okay. Can I multiply A and B by 2? No. But can I multiply A, B, and C by 2? Yes, I can, because if AX1, BX2, C equals 0, and I multiply both sides of this equation by 2, I'm just going to get 2AX1 plus 2AX2 plus 2C equals 0. And that's still going to be true. So even the implicit representation is not. If I want to test whether or not two lines are equal, I have to do something special, like force one of these coefficients so that I can take away the ability to scale. If, for example, I choose the value such that C has to equal 1, then I've normalized things. But I have a problem if I do that. If I try and force C equals to 1, what happens? Well, what happens if the line doesn't actually have a value of C? If C is equal to 0, I can't divide by C. I can't talk about A over C, B over C, C over C, if C equals 0. So actually trying to normalize them is difficult. So, but this conversion process gives us a nice way of also seeing why two lines, you can have two very different representations of the same line in parametric or now in implicit form. We'll see this both. Okay, so now let's move on to another important thing we want to be able to do with a line. We want to be able to measure the distance of a point to a line. So imagine that we want to have a robot traveling along the line, say a corridor, and we want to know how far we've gotten away from that as we've gone through it. And we need to make sure that we don't get too close to the wall, so we have to have some distances before we would run into the walls and have problems. So we can talk about the smallest distance of a point to a line. And it turns out that there's a nice property that for a line, the smallest distance of that point to the line is perpendicular to the line. And to sort of see this geometrically, imagine that it wasn't perpendicular. Choose some other point. Well, then I could always represent that point as some distance perpendicular plus some distance along the line. Okay, and then of course we're talking about the hypotenuse because that's the distance along that. But the hypotenuse is always longer than the axis along the perpendicular side. So we'd get a contradiction. So we know that the perpendicular distance to the line is always the smallest distance. And then we can use that to now talk about how do we compute the distance of a point to that line. So if we start with an implicit representation, ax1 plus bx2 plus c and some point r, now I can ask what is the value of d, which we've talked about before, which is just a dot r minus p divided by the norm of a, which we can write out. I can then ask the question, well, what happens if I take some other point w? That would be r minus p, and we know that its dot product of a dot w is the norm of a times the norm of b times the cosine theta of the angle between them. Okay, so cosine theta is equal to d divided by w, again just from geometric construction. Right. Cosine of this is w divided by that, right, Sakatoa. And then, since we know what v is already, that'll say that d. Now we can also talk about, see how we can compute the distance of a point to a line using parametric representations. So start with our parametric representation. Okay, we're going to let w equals r minus p. So p is the point in our parametric representation. R is the point I want to compute the distance to the line for. And so now I can build a triangle, considering the perpendicular here, then the angle alpha. Okay, so if this is the perpendicular, I know that the magnitude of w times sine of alpha, this angle here, will give me the distance d, right? Again, that's from Sakatoa. Sine is opposite over hypotenuse. Sine is opposite over hypotenuse. Just bring them back over on the side. We also know from trigonometric identities that sine alpha is equal to the square root of 1 minus cosine squared of alpha. And we know from the dot product how to get cosine. Cosine of alpha is equal to v dot w divided by the norm of v and the norm of w. So this gives us now a formula for cosine. We can stick that in, and from that we can get a formula from sine. Okay. So a little bit more complicated, but in the end, right, we have from either parametric representation or implicit, we can compute the distance of a point to a line. So we don't have to convert between them just to be able to compute distances. One is just a little bit more complicated formula. Although here we have a sine, remember, since we're going to pop this in, we can actually look at this as the magnitude of v times the square root of 1 minus v dot w divided by the magnitude of v magnitude of w. So we can actually compute the distance without ever computing sines and cosines, because we're just going to compute the dot product and the lengths of some vectors, okay, and then stick a square root. So we have one square root to deal with here. Okay, so this idea of the closest point is useful, and in fact, the idea of which point on the line is the closest is a useful term that we will use in lots of different problems later in the semester. And so this point has a special name. We call it the foot of the point. So given a point, the projection of that point onto the line is its foot. Okay, and so you can think of this again from lots of different applications where you want to find the point that is closest on a line. And since we know how to compute the distance, it turns out that finding the foot is pretty much the same. In fact, if I want to find it given a parametric representation, what we really want to do is find the parameter t such that p plus vt equals q, where q is the foot. So if I know what that distance is, I can then be given q. Okay, so if we define w, the distance to that point, okay, we know r minus p is our w. We're now going to go back and look at what we got. Cosine of this angle is the magnitude of v of t times v divided by w. Right. Where'd the t come from? Well, remember, t is how we're defining q. Q is p plus t times v. But we also know that the cosine of that is got to equal to v dot w divided by the magnitude of v, the magnitude of w. We solve this, so now I can look at this here as an equation. Magnitude of tv divided by magnitude of w equals v dot w divided by magnitude of v, magnitude of w. I can actually cancel the magnitudes of w's as long as it's not 0. and then solve, and I'll get that t is equal to v dot w divided by the magnitude square, magnitude of v squared. Now to do that, I have to take v outside this magnitude symbol. Why am I allowed to do that? Well, remember, t is a scalar, and scalars times vectors in terms of their magnitude is just the magnitude of the vector times the scalar. So that lets us solve for t. This will give us the value along the line v, and therefore I can then compute q and get the foot of a point. Find the closest point on a line to another point. A special case of playing with this kinds of closest points are dealing with intersections. Okay, and again, this has lots of interesting things we can do with it, trying to figure out when a line is going to intersect. So if I'm working and I try and figure out when my path will cross some other path, we're assuming we're both moving on straight lines, that's an intersection question. If I'm trying to figure out when profit, assuming a linear growth, is equal to losses and my break-even point, that would be two linears. That's a point of intersection. So we can ask questions like, do lines intersect? At what point do they intersect if they do? And what is the value of one or both of the lines when they intersect? That is, what is the point of intersection? And these kinds of questions plus the line representations give us some questions. What's the best method? What's the best representation to answer each of those questions? You can actually answer them with either question because you can always convert from one to the other, but sometimes it's more natural. So let's look at parametric and implicit representations. If I want to find the intersection point I can solve for that in the parametric representation by basically taking the parametric representation of the first line, a p1 plus t v1 plus b p2 plus v2, and equal to 0. So, sorry, here I'm doing it with the implicit. I've taken the parametric representation of one line and the implicit of the other, and I'm basically sticking the parametric into the implicit representations, working it out, and solving for t. Okay. So now what happens if the lines are parallel? Well, if the lines are parallel, this value here, a v1 plus b v2 will be 0, and t will not be well defined. It'll go off to infinity. So given one representation and another, you basically stick the parametric into the implicit. You can find out where they intersect. Before you actually solve for t, it's recommended that you compute if a v1 plus b v2 is equal to 0, because if it is, then the lines are parallel and there is no point of intersection. What about if they're both parametric? Well, if they're both parametric, then you want to find parameters s and t such that p plus v, t times v plus q times, or q plus s times w is the same. So you're going to find this parametric representation, that parametric representation, and you want to find a point such that they're equal to each other. So you can write that out and you get t times v minus s times w is equal to q minus p, and that gives us a set of two equations and two unknowns, which you can solve. How? Well, we'll talk about how to solve 2 by 2 equations later, but you can always do this by hand and figure out how to solve this. So both parametric representations can solve this, it's just a little bit more complicated. So if v1 and w are linearly independent, this 2 by 2 set of equations will have no solution. What does it mean if v and w are linearly dependent? V and w are the vectors. Well, if they're linearly dependent, then we've already seen that for vectors they're linearly dependent, like if they point in the same direction, which means the lines are parallel. So you can't find the point of intersection of two parallel lines. Okay, what if they're both implicit? Well, if they're both implicit, we have these two representations, and then we want to find the intersection point that satisfies both sets of equations simultaneously. So we again get two equations and two unknowns. And if the lines are parallel, then A and A bar will be linearly dependent. That is, their normals will be linearly dependent. Now in this case, they don't have to be the same. They could be pointing in opposite directions. Their normals don't have to be in the same direction. They can be anti-parallel, and they'll still be linearly dependent. Okay, so that gives us three solutions. If both are implicit, we end up with two equations and two unknowns. If both are parametric, you get two equations and two unknowns. And if you have one in parametric and one implicit, you get a direct formula for t. Notice this also tells you a way, if you're given two parametric or two implicit, convert from one to the other, and you don't even have to worry about how to solve two equations, because for one parametric plus one implicit, it's easy to solve. You're inserting one into the other. Okay, so that's it for lines. Make sure as you review the chapter, go back, you understand parametric representations, linear interpolations, point normal form, the implicit form of a line, the explicit form of a line, and why we're not going to actually use it too much. How to define a line through 2 points, how to define a line with a point and a vector, parallel to the line, how to define a line with a point and vector perpendicular, how to convert between different forms of a line, compute the distance to a point, distance of a point to the line with a foot, or the intersection. These are all tasks you should be able to cover it. And so consider some example problems from the end of the chapter. Given a parametric form of a line defined by 2 points, such that L of 0 is P and L of 1 is Q, give us the parametric representation of that line. Okay, and of course you should be able to do that if a change P and Q shouldn't make any difference. So make sure you've practiced 1 or 2 of those. And if we look back at those, you might also be able to answer whether or not any of those representations formed a convex combination. You also want to be able to find the equation for a line in implicit form that passes through a particular set of points, or test if points lie on a particular line. Both of those are fair game for what we need to be able to discuss in class. Figure out how to convert from implicit to parametric, or parametric to implicit, and from parametric from implicit. So those are some of the kinds of questions we will be going over in class on Thursday.